Welcome to this analytical teardown. Today, we are critically evaluating a major proposition emerging from the semiconductor sector, Huawei's so-called Tau scaling law. Introduced by chief chip architect Ting-Bo He, this concept is being heavily promoted as a defining principle for modern hardware progression. But as we strip away the corporate presentation, we find an idea that completely fails the foundational test of semiconductor physics. Let's break down exactly why this claimed law is actually nothing more than an undefined slogan. Pause. To understand where this proposition falls apart, we first have to examine the context in which it was introduced and the core thesis it attempts to present to the semiconductor industry. Let's put the proposal side by side with the absolute gold standard of industry observations, Moore's law. Moore's law succeeded because it was structurally sound. It described a single spatial variable, lithographic feature size reduction, where shrinking components mathematically dictated an exponential doubling of transistor density roughly every 2 years. It was physically driven, precisely measurable, and entirely falsifiable. Now look at Ting-Bo He's Tau scaling. It tries to jump straight to describing temporal performance over time, yet it provides no defined physical mechanism, no concrete mathematical formula, no empirical baseline curve, and no predictive model. It references a latent time constant, tau, without actually telling us how to measure it. While the official presentation masks the core theory in high-level rhetoric, we need to extract what is actually being claimed. For Tau scaling to genuinely function as a valid scientific or engineering law, it relies on 5 deeply flawed underlying assumptions. Let's isolate these 5 unproven assumptions. First, it claims a single characteristic time constant can magically govern all multivariable hardware timing. Second, it assumes performance tracks a smooth, predictable exponential growth curve. Third, it posits that this constant remains universally stable across radically different microarchitectures, memory layouts, and process nodes. Fourth, it assumes the concept holds genuine predictive value to guide real-world engineering constraints. And fifth, it relies heavily on the historical prestige of Moore's law as a rhetorical anchor. None of these claims have been proven, and they form the exact targets for our physical teardown. Now, let's look at the hard technical weaknesses where this conceptual framework completely breaks down under real-world semiconductor physics. The first structural problem is a massive category error regarding hardware variables. Moore's law worked because spatial scaling had one clear dominant variable, geometric feature size. Hardware timing, however, is a radically different beast. It is an emergent property dictated by an endless web of tightly closed, nonlinear interdependencies. When you shrink a transistor, you don't just change speed cleanly. You introduce worse wire delay, localized thermal limits, RC delays, packaging bottlenecks, and intense voltage scaling challenges. These independent variables scale at completely different rates and often scale directly against one another. Because of this, trying to collapse a web of messy, opposing physical limits into a single neat constant like tau is not just an oversimplification, it is structurally impossible without throwing out basic semiconductor physics. Furthermore, a genuine scientific law requires foundational criteria. It demands a clearly measurable quantity, a concrete functional form, a comprehensive dataset, cross-generational validation, and complete falsifiability. Tau scaling possesses absolutely none of these. If we chart what is actually happening in modern silicon over time, we see that hardware time constants are not beautifully converging into a single unified trend line. They are radically diverging. The industry is aggressively running face-first into the memory wall, devastating wire delays, severe thermal density limits, and a total stagnation in raw frequency scaling. To assert that these diverging physical architectural walls collapse into a single variable is an active denial of engineering reality. This brings us to what we call the narrative temptation. Because Moore's Law is so iconic, global technology corporations face an intense marketing urge to label abstract market trends as historical laws to signal technological leadership and spin a compelling corporate story. But naming a trend doesn't make it a physical reality. A speculative, non-operational Tau law offers absolutely zero actionable engineering value. It does not give engineers a roadmap to solve the brutal, localized operational bottlenecks currently facing Huawei, namely multi-die packaging constraints, interconnect limits, memory bandwidth, power delivery efficiency, and severe manufacturing yield variations. Let us step back and look directly at the underlying logical errors and architectural fallacies driving this entire proposition. This comparative synthesis matrix clearly highlights the core logical divide. Moore's law operates in the stable domain of geometry and physical space, where lithographic limits act as a single dominant driver. Conversely, Tau scaling tries to dictate a law of time. But time in a high-performance chip is not an independent physical input. It is a highly volatile, highly complex emergent outcome resulting from the chaotic interplay of electrical, thermal, manufacturing, and architectural subsystems. Put simply, you can have a predictable law governing physical space, but you cannot dictate a clean law of time across a multivariable, highly complex computing system. When you try to map interconnect delays, severe memory bandwidth caps, thermal densities, and power delivery drop-offs, you are looking at a highly complex, multi-dimensional system. The fundamental scientific failure of Tau scaling is that it makes a classic category mistake. It forces this multi-dimensional reality down into a single highly abstract temporal symbol, Tau. In doing so, it strips away, ignores, and entirely loses the actual physical mechanisms that determine hardware evolution. We have mapped out the claims, the technical contradictions, and the structural logical errors. Let's look at the definitive final status of this proposal. To conclude our teardown, we assign 3 definitive statuses to this concept. First, there is absolutely zero empirical grounding. It uses heavy rhetorical phrasing to sound scientific, but contains no functional equations or actionable mechanics. Second, it is an absolute category error that completely fails at the level of core physics by treating an emergent temporal system as an independent basic variable. And third, it holds no real engineering value, offering zero operational clarity for solving real-world interconnect or silicon packaging crises. When we strip away the corporate presentation, the verdict is undeniable. Tingbo He's Tau scaling is not a law. It is simply an undefined marketing slogan. We are now diving into the supplementary notes and visual addendum for our structural teardown of the Tau scaling proposition. While our core physics critique stands completely on its own, this addendum is designed to explore the broader conceptual landscape surrounding semiconductor scaling. Our goal here is to clarify the logical patterns underlying recent corporate claims, expose the foundational ideas framing the current discussion, and provide an analytical toolkit for evaluating similar technology claims in the future. Let us begin with Section 6, where we isolate the core fallacies and distinct breaks in logic that occur when marketing narratives collide with rigorous physical laws. We will categorize these logical failures into 3 distinct groups, starting with Group 1, which focuses on evidential and structural flaws within the Tau scaling argument itself. Group 1 contains 3 massive structural errors. First is a false analogy, which attempts to treat fundamentally different domains as comparable by mapping multivariable temporal behavior directly onto Moore's law, a single spatial variable. This creates a dangerous illusion of scientific legitimacy where no shared structure exists. Second is severe oversimplification, which collapses dozens of tightly interacting hardware time constants down into one single symbol, obscuring the true physical boundaries and misleading engineering decisions. Third is non-falsifiability. By attributing any real-world deviation from the trend to vague external factors, the claim becomes immune to empirical refutation. A trend that cannot be proven wrong is a marketing slogan, not a scientific law. Moving into Group 2, we shift our focus from structural layout errors to deep conceptual confusions regarding basic hardware behaviors. Group 2 reveals 3 distinct conceptual errors. It begins with a category mistake, where temporal performance, which is an emergent, multivariable outcome, is incorrectly treated as if it were basic geometric scaling. This misclassification inevitably leads to invalid conclusions. Next is reification, where the abstract placeholder symbol tau is spoken about as if it were an objective physical constant of nature, giving it unearned rhetorical weight without any actual grounding in semiconductor physics. Finally, the framework mistakes correlates for causes. It attributes general industry performance improvements to the existence of tau itself, completely ignoring the specific engineering breakthroughs that actually drove those gains. Misattributing cause like this makes it impossible to accurately diagnose real-world hardware bottlenecks. Next, Group 3 deals with inflated reasoning, analyzing how corporate storytelling systematically overstates theoretical value. Group 3 outlines the rhetorical tools used to inflate these claims. We see explanatory inflation, which adds immense theoretical weight by declaring a law without offering a single new predictive or engineering insight. This serves only to obscure the real architectural problems. Then comes narrative reductionism, which packages highly complex silicon evolution into a clean, digestible corporate story. While simple stories can motivate a workforce, they cannot replace actual physics. Finally, there is a heavy appeal to intuition, which pushes the idea that time constants should scale simply because it feels neatly analogous to spatial scaling. But personal intuition is never a valid substitute for hard physical measurement. In Section 7, we leave the logical errors behind and focus on the essential, real-world terminology and physical constraints that define modern chip manufacturing. Let us look at the hard physical limiters. First is wire delay. As lithographic features shrink, the resistance-capacitance delay of local interconnects grows at a disproportionate rate. Today, wire delay is a dominant barrier to processor performance, and it absolutely does not scale in a uniform manner. Second are thermal density limits. The ongoing inability to safely dissipate trapped heat as transistor counts increase has completely halted raw clock frequency scaling. These thermal walls are sudden and absolute. They completely defy smooth, exponential performance curves. So, next, we must address the memory wall. This represents the widening performance gap between raw core processing speed and actual off-chip memory latency and bandwidth. This critical architectural bottleneck is highly dynamic and cannot be neatly captured by a single static time constant. Furthermore, look at modern packaging and interconnect architecture. The vast majority of performance gains today are realized through advanced multi-die packaging, such as chiplets, rather than traditional front-end transistor scaling. Advanced packaging topologies do not follow or obey a single temporal constant. This brings us to the core technical reality of multivariable temporal scaling. Time and delay paths within modern silicon are dictated by dozens of cross-dependent architectural factors. This messy, non-separable reality is the primary reason temporal performance cannot be formalized into a clean scientific law. Compounding this is process variation. Severe manufacturing and material variability fundamentally alters localized timing, power consumption, and wafer yields. This variation introduces highly non-uniform scaling behaviors across separate chips and fabrication runs, completely defying pure mathematical predictions. We conclude with the absolute necessity of scientific validation. In engineering, operationalization means turning an abstract idea into something clearly measurable, testable, and repeatable. Because the tau scaling proposition completely lacks an operational definition or measurable primitives, it cannot be validated by the semiconductor community. Without that validation, it remains an undefined corporate slogan.